Hello and welcome to our lesson on continuity. This is going to be from section 2.5 in our calculus text. Let's get started. The first thing we have is the definition of continuity. If we could zoom in on this definition so you can see it clearly. It says a function is considered to be continuous at a number a if, and then notice what the requirement is. The limit of the function as x approaches a has to equal the function value. Now this statement inherently implies that three conditions must be met. And here are the three conditions. F of a has to be defined. That means the function value at a must exist. And number two, the limit of the function also has to exist. The third criteria is that once the first two conditions have been met, then they must be the same. So the definition of continuity, in order for a function to be continuous at a number a, not only does the function have to be defined at a, not only does the limit have to exist as x approaches a, but they have to be identical. The limit of the function as x approaches a must equal the function value at a. So for our first example, it says at which numbers for this function that's graphed is the function discontinuous. In other words, we want to know where is this function not continuous, and then we want to state why. Now the why is going to be you listing at which of the three criteria it fails. And our first number that we need to look at is 1. Notice when x is 1, the limit does exist because we approach the same height from the left and the right, but there is no graph. In other words, there's an open circle, so the graph doesn't exist there, and there's no actual point like over here. There's no solid dot to indicate what that function value is. So our first answer would be x equal 1, and then because. This is my abbreviation for because. We would say that f of 1 does not exist. That function value doesn't exist. That's why it's not continuous. Our next function value that we need to consider is 3. Notice this solid dot down here says that f of 3 exists, but since we are approaching a different height from the left and the right, then the limit doesn't exist. So next we would say x equal 3 is a point of discontinuity because the limit as x approaches 3 of the function does not exist. And the last point of consideration here is 5. Notice that the limit exists. As we approach 5 from the left and the right, we are approaching the same height. Notice there is a solid dot up here, so f of 5 does exist. There is a function value at 5. The problem is that this function value is not the same as what the limit is. Therefore, we would say x equal 5 is also a point of discontinuity because the limit as x approaches 5 of the function does not equal the function value at 5. They are not at the same height. They don't have the same y, and so this is why the function is not continuous. Our next example to look at, we have functions that we need to consider it says, where are each of the following functions discontinuous? So we know that these functions are going to have a point of discontinuity. They want to know where does that occur at. So for our first function here, notice that this is a rational function, and rational functions have the restriction that the denominator cannot be 0. So if we set the denominator equal to 0 and solve, we can see that there will be a point of discontinuity at 2, because that is also where the vertical asymptote occurs. Does that make sense? F of 2 does not exist because the function would be undefined at 2. Next, notice we have the same rational function. Next, notice we have the same rational function, but now it's part of a piecewise function where they take care of the fact that x is not continuous at 2 for the rational part, and they give it a function value for when x is 2. So now what we know is, we know that f of 2 exists. We can see that f of 2 is defined. The next thing we need to consider is, does the limit of this function exist as x approaches 2? We could care less that the rational function up top, we could care less that it doesn't exist at 2, because the limit doesn't care about what happens when you get to 2. It only cares about what happens as you approach 2 from both sides. So next we're going to look at the limit as x approaches 2 of f of x. Next, we want to consider the piecewise function that has our initial rational function as part of its piecewise function. Notice here in the second part, they take care of the undefined situation that we had previously. So now we can say that f of 2 is defined. They have stated that f of 2 is 1. So that is our first criteria that is met for continuity. The next criteria that we need to check is the limit as x approaches 2 of our function. Now there's a couple of ways that we could evaluate this limit. We could make a table, we could look at the graph. What I'm going to do is see if I can eliminate the undefined situation so that I can simply do function evaluation. Notice that the numerator does factor. It's going to factor as x minus 2, x plus 1, all over x minus 2, where we can see we have a common factor. Not only do those factors eliminate, but that does eliminate the divide by 0 error that we run into with direct substitution. And so now we can just plug and play. 2 plus 1 is 3, and we can see that this limit does exist. If we go to Desmos, we can verify that. I have graphed our function, and as x approaches 2 from the left and the right, we can see that we are approaching a y value of 3. So that means that Desmos verifies our arithmetic. And then what we need to notice is that the limit of the function exists and the function value exists, but those are not the same. And so this function, this piecewise function, would be discontinuous at 2. And the reason is because the limit of the function as x approaches 2 does not equal the function value at 2. Our next example, we have another piecewise function. Both of these pieces are going to be continuous everywhere because they, everywhere. Everywhere on their domain. And I didn't state that previously, but we know that a rational function is going to be continuous everywhere on its domain. And here we can see in the previous problem that the domain was restricted, saying that x could not be 2 for the rational part. In this example, we can see that the restriction eliminates the divide by 0 error, so a rational function is going to be continuous everywhere on its domain. So the only place that we need to be careful about discontinuity is at the transition point. And again, I didn't state this before, but on a piecewise function, provided that we know that both pieces are continuous on their domain, the only point that you have to be concerned about then is the transition point. So for our example, f of 0 is defined. They have defined the function value at 0 to be 1, so that criteria is met. The next criteria that must be met is the limit as x approaches 0 of the function must exist. It must equal some number L, like a real number. And so what we can do is we can make a table for our 1 over x squared part and look at what happens as we approach 0 from the left and the right, and see if that does approach some value. And the easiest way to do that here is with Desmos. Notice that as we approach 0 from the left and the right, this function, the y values, are just getting infinitely high. So this limit is infinity because we do approach positive infinity from both sides, but infinity is not a number, and so technically this limit does not exist. So we can say that this function is not continuous at 0, and the reason is because the limit as x approaches 0 of the function does not exist. And for our last function, if you're unfamiliar with this function, this is called the greatest integer function, also known as the step function. And what happens here, if you think graphically about the greatest integer function, or if you don't know how it works, it says that when you plug in a 0, you get 0. And when you plug in any decimal value up to 1, you get 0. But as soon as you get to 1, the graph steps up to 1 and will remain at a height of 1 until you get to 2, where it will then step up to 2. This is how the greatest integer function works. Now remember, we're trying to decide where is it discontinuous, and we notice that this function is going to be discontinuous at every integer value because that is where the step occurs. Okay, so this function is defined at every integer because there is a solid dot at the integers. However, if you consider the limit, say in this case, let's consider the limit as x approaches 1 of the greatest integer function. What you're going to approach from the left is a height of 0, but from the right, you're approaching a height of 1. So the limit is not going to exist because you don't approach the same height from the left and the right. Now, how do you write the notation to indicate the function is discontinuous at all integer values of x? We're going to use set notation for that, okay? So we would say the function is discontinuous for the set of all x's such that x is an element of the integers. And we're going to use the fancy notation in this class. This funky looking z with 2 backbones is the symbol we use for integers. And so this is the way that you would indicate the set of all x's where this function will not be continuous. The next definition we want to look at is continuity from the left and the right. This says that a function can be continuous from the right at a number a if the limit as x approaches a from the right of the function equals the function value. And from the left, it is possible for a function to be continuous from the left if the limit of the function as x approaches a from the left is the same as the function value at a. That is all this definition says, is that if you're coming in from the left or the right and the function is approaching the height and the function value exists and they're the same, then it would be continuous from one side or the other. Next, we have a definition that says a function f is continuous on an interval if it is continuous at every number in the interval. If f is defined only on one side of an endpoint of the interval, we understand continuous at the endpoint to mean continuous from the right or continuous from the left. Next, couple of theorems. Any polynomial is continuous everywhere. So polynomial functions are continuous on the reals from minus infinity to infinity. Any rational function is continuous everywhere it is defined. That means that you can consider a rational function to be continuous everywhere but at its restriction. Everywhere over the domain of the rational function. And then another theorem says the following types of functions are continuous at every number, and then it's important to realize that when they say on their domains. So if any of these functions have a restricted domain, what this is saying is that it will be continuous, but only on the domain of the function. And a couple of those to point out would be like for root functions, specifically a square root function, which if you remember the graph of a square root function, makes it like a swoosh. These functions will have no break in the graph from start to finish, okay? They will be continuous everywhere that the function is defined. Next theorem, if f is continuous at b, and the limit as x approaches a of some g of x is b, then the limit as x approaches a of the composition of functions will be the same as the function value at b. Okay, in other words, it says if you're taking the limit as x approaches a of a composition of functions, provided that this criteria is met, you can take the limit of the inner function and then evaluate the outer function at the limit value. That's what this says. Next, another theorem. If G is continuous at A and F is continuous at G of A, then the composite function G then the composite function f circle G given by this notation will be continuous at A. And then we reach one of the big ones. This one is important to know, the intermediate value theorem. Suppose f is continuous on the closed interval from A to B. Okay, so we're going to say that f is a continuous function on a particular closed interval, which includes the endpoints. And let n be any number between f of A and f of B. So n would have to be a y value since f of A and f of B are y values. Notice this restriction that the endpoints of the interval cannot be at the same height. It says if all of this criteria is met, then there will exist a number c on the open interval AB. Notice that makes C an X value because A comma B would be from an X1 to an X2, where f of C will equal n. So if we slide to the right here just for a second and consider a graphical representation of what this says, we could have some function, it doesn't matter, some function f of x, which is continuous from, let's say, from A to B here, okay? Where f of A and f of B are not at the same height. What this says, what this what the intermediate value theorem says is that there will be some number n between f of A and f of B such that, there will be a c on the interval from A to B such that the function value of c will equal the n that you choose, provided that you choose an n, a number between f of A and f of B. There will exist a number between A and B that has the function value of the number that you request. All right, we have some examples to look at here to illustrate the intermediate value theorem. Use the intermediate value theorem to show that there is a solution. Okay, this is the sticky part. A solution, remember, graphically is represented by an x-intercept. An x-intercept of a function is the solution of the equation. We know that x-intercepts occur when y is 0. So if we're going to use the intermediate value theorem to determine if there's a solution, what we want to show is that somewhere on the interval given, there will be a number where y is 0. Now let's see if this is obvious to you. If f of -1 works out to be negative, I'm saying if it does, and f of 0 works out to be positive, would it make sense that the only way that you can go from below the x-axis to above the x-axis is to cross the x-axis? That should make sense to you. And where it crosses the x-axis will be where y is 0. Now, we're not finding the solution. We're simply finding if there is a solution on the interval. Okay, and this is the gist of what we're going to do. This is the basic instruction that you're going to calculate the function values at the endpoints, and if they produce opposite sign y values, that is going to indicate that there is a solution on the interval. All right, so here we go. 55. Notice that we have an equation that is equal to 0, and the intermediate value requires that we have a function. So what you need to know is that you can take an equation and represent it as a function if and only if it's equal to 0. And in that case, we can say that the function would be negative x cubed plus 4x plus 1. Now in the equation it says equal to 0. That's our y value. So we want to know, where is y 0? That would be what we would ask if we were looking for the solution. Here we simply want to determine if there is a solution on this interval. So we need to calculate f of -1 and then calculate f of 0, and if those are opposite sign, then we will know that there has to be a solution. And not to bore you with the tedious work, but here are the function values worked out, where we can see that f of -1 produces -2, f of 0 is 1. Those do have opposite signs, and so therefore we can conclude, we can say, yes, there will be a solution on this interval based on the intermediate value theorem. Next, for problem 56, our equation is not equal to 0, and so we need to make it equal to 0. What I'm going to do is move the natural log of x to the other side, which would make this side 0, and that would make our function x minus the square root of x minus natural log of x. And then we would then need to evaluate the function at the endpoints, calculating f of 2 and f of 3. Remember, those need to work out to be opposite sign values in order to indicate that there will be a solution on that interval. And again, not to bore you with the calculations, but here is the work showing that f of 2 produces a negative y value, f of 3 produces a positive y value, since those are opposite sign. And I might mention it doesn't matter what order they're in, they just have to be opposite. This would imply again that yes, this would imply again that yes, there is a solution on the interval based on the intermediate value theorem. Next, we have another example. It says, for what value of the constant in this piecewise function will the function be continuous over all real numbers? And if I didn't make it clear before, let me state that the main point of concern for a piecewise function is the transition point. The first piece and the second piece of this piecewise function are polynomial, So we know that those pieces are guaranteed to be continuous on their domain. We are concerned with the transition point, okay? So here's what we know. We know that when this graph transitions from the top piece to the bottom piece, they must be at the same height. And so what we're going to do is we're going to plug in the transition point for X into both pieces. We're going to set them equal because those Y values will need to be equal. So we will have C times 2x squared plus 2 times 2. That is the top piece evaluated at 2. And the bottom piece evaluated at 2. 2 cubed minus C times 2. And then if we solve for C, we'll know for what value C must be to make sure that this function is continuous at x equal 2. So simplifying, we get 4c plus 4 equals 8 minus 2c. Then bringing the negative 2c one way and the 4 the other is going to give us 6c equals 4. Dividing both sides by 6. We're going to end up with a fraction which reduces to 2/3, which is our answer. That is what C needs to be to guarantee continuity over x equal 2. And one more example using a piecewise function that's way more interesting. Here we have 3 pieces of a piecewise function which creates 2 transition points. And so the first 2 pieces are going to have the same y value when x is 2. And then the second 2 pieces are going to have the same y value when x is 3. Okay, so that's going to be 2 different equations. Notice that we do have 2 unknowns, a and b. And if you remember anything about systems of equations, you have to have the same number of equations as you have unknowns in order to find the solution. So let's set up our equations. First, plugging 2 into the top part. Well, you can't do that because you get an undefined situation. Again, let me bring that over here and illustrate that if you consider the rational part of the function, if you evaluate this at 2, that's going to create a divide by 0 error. But we have good algebra skills. We can factor the numerator knowing that it's the difference of squares. And since we can eliminate the undefined situation, we can calculate, in this case, the limit with evaluation. So replacing x with 2, we can see that this is approaching a height of 4. Which means that the second piece of the function would have to pick up at a height of 4 and keep going. So the second equation evaluated at 2 would be a times 2 squared minus b times 2 plus 3. And remember I said when x is 2, it's going to have to be at the same height that the previous piece was as it approached 2, and so we know this is going to have to equal to 4. This is one of our equations. Now the second equation is going to occur at the second transition point, which would give us a times 3 squared minus b times 3 plus 3, that has to equal the bottom piece, also evaluated at 3. So we're going to take these 2 equations and we're going to simplify and reevaluate once we get those simplified. And here we are. This equation simplified to 4a minus 2b plus 3 equals 4. The second equation simplified to 9a minus 3b plus 3 equals 12 minus A plus B. Since we have a system of linear equations in two variables, what we need to do is put these in standard form. In the first equation, I'm going to move the 3 over, which will get the A and the B by themselves on one side. In the second equation, I'm going to bring the negative A and the positive B to the left, and then bring the positive 3 to the right. And that will give me 4A minus 2B equals 1. That's from the first equation. And the second equation, I will have 10A minus 4B equals 9. If I do all of the algebra there, relocating the pieces. Now, consider this set of equations. If I want to solve for A and B, I'm seeing that the easiest way to do that would be with the elimination method, also known as the addition method. If I take the first equation and multiply through by negative 2, notice that that will give me a positive 4B. When added to negative 4B, I can eliminate the B's. So let's rewrite our equations after we distribute the negative 2 and use the elimination method. Here we go. Negative 8A plus 4B equals negative 2. The bottom equation is unaltered, so we just copy and paste, and then we use the addition method. 10 minus 8, that's 2A. B's cancel. 9 minus 2 is 7. And we can see that we're going to get an improper fraction for A. And that's okay. It doesn't have to be an integer. But now that is the answer for A. I also need B. And so we can take this back and plug this into either the first or the second equation for A and solve for B. I choose the first equation. 4 times A would be 4 times 7 halves minus 2B equals 1. 2 goes into 4 2 times, giving me 14 minus 2B equals 1. Moving the 14 makes it negative, which leads me to negative 2B equals to negative 13. Dividing by negative 2 is going to isolate the B. Okay, so writing these nicely. A is 7 halves. B would be positive 13 halves. And that's going to answer the question that they initially asked. What would be the values of A and B to guarantee continuity? And that's going to do it for this lesson. So if you have any questions or comments about anything covered in this video, please feel free to leave those in the comment section below, or you can text me. And thanks for watching.